Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Finland. And I study cosmology. I'm a cosmologist. That means that I study the universe, the contents of the universe, how it all evolves, how it all interacts, all of the cool stuff happening inside the universe. And I love being a cosmologist. I love coming here and chatting to everybody about all of the cool things happening in space. Hey, Scott. Hey, David. Hey, other David. Great to see all of you coming in. Great to see all of the regulars joining. Welcome back, everybody. I know Cup of Cosmology has been away for a few weeks. I've been traveling and been doing stuff. But now we're back and we're kicking off this middle of the second month of the year relaunch, whatever you want to call it, with what I'm expecting to be a very fun show today. Today's topic is general relativity. And before we jump into that, as always, please do like the video, leave a comment, subscribe to the channel if you haven't done so already. All of this really, really helps. Please do all of the usual YouTube engagement things. I do really appreciate it. Okay, so we have a very long title today. This is a fun topic, and it's not a topic I'm going to cover alone. So I have two guests with me today, and I'm going to bring both of them up on screen. So hello, Ali. Hello, Lorenzo. Welcome to Cup of Cosmology.
Hello.
Hi, Diana. Thanks for having us.
Yeah, so both Ali and Lorenzo have been on Cup of Cosmology before. They are return guests now. This time we get them both together. So before we jump into quirks and creativity in general relativity and why we have this fun title, do you two want to introduce yourselves? Ali, do you want to go first, just because you're on my left?
Yeah, sure. So I'm a PhD in theoretical physics at University of Helsinki. I like general relativity. I think it's quite cool. And I suggested that we all suggested that we have this talk. And the title was supposed to rhyme because all good things in life always rhyme. And it's nice to be back on the show. And it was a nice excuse to come back. So.
Yes, for the first few weeks, I was insisting that I was not going to go with this title and we needed another one. And Ali insisted so much that we ended up with quirks and creativity in general relativity. You have Ali to thank for the title.
You're welcome.
Lorenzo, do you want to introduce yourself?
Yes. Hi, I'm a theoretical physicist here in Helsinki University. He brought me here. He basically forced me to come. Has the schedule for all my summer, so here I have to come here because I also very like generalities this aspect, even if I'm not working. Yeah, I'm always super happy to talk about that.
Yeah, so you see, when I think of quirks and creativity in general relativity, the things that come to mind for me are things like paradoxes and spaghettification and particle emission around black holes. But apparently these guys come up with much more complicated things and have sent me about 10 pages of notes. So we have a lot of stuff to cover. I think Ali wants to start with something to do with thermodynamics. And as always, before we jump into this, you can ask all your questions. We will do our best to try to answer them. Of course, we don't have all the answers, but with three of us here, I'm sure we can brainstorm something that sounds like a credible answer and hopefully actually is a credible answer. But Ali, I think you wanted to start with something about thermodynamics, if I'm not mistaken.
Yes. So, okay. The first cool thing that we thought we would speak about is what happens when something falls into a black hole. So,
which is a cool question.
Which is, of course, a very cool question. So, Lorenzo, who is the one, by the way, who wrote the 10-page notes? I have to say, I give him full credit. I didn't write anything, but okay.
I'm sure.
I don't know if you can see the board, but okay. If this is like a black hole, and this is a shell that we throw inside the black hole.
I think if you draw it slightly bigger or move the laptop closer, then people will see it more.
Yeah. Okay, so we have a black hole. Is this visible?
It's visible. We have an important question from David here, from David Howden, saying, will all the explanations also be in verse, given that the title is rhyming? And I honestly did propose this, and I was overruled.
Yeah, I cannot freestyle. I can try, but I'm sorry.
If anyone wants to start beatboxing, I'm all for it. Let's go. So Ali, thermodynamics may or may not rhyme. Or okay. What happens when we fall into a black hole?
So hopefully you don't fall in, but you throw a chair. So you get a chair, one of those nice chairs that we have here, and I throw one of them into the black hole. And what happens is, well, the entropy of the universe outside the black hole decreases. But why does the entropy decrease? And what is entropy anyway?
All good questions.
These are all good questions that I don't know the answer to.
Okay, so
Okay, so Lorenzo will come and explain to me.
I think Lorenzo's going to go and tell Ali what is happening. This is absolutely not a rehearsed sketch in any way. This would have looked so smooth if done properly.
Yes, and I think he should have left his laptop there, but anyway.
Okay, Lorenzo's gone for a walk, so I've just removed Lorenzo, and in a completely unexpected turn of events, people are actually in the same room. Okay, so now that we have you both together, we were going to ask the question of what is entropy.
Do we have the slides that I sent you? Do you think we can share that?
Do you want one of the images, or do you want
if you can share the images, that would be cool.
Okay, give me 1 sec, because that is somehow actually not ready.
But I think, like, from the screen, I cannot see very well the board, so it's probably better if we have some picture.
Yeah. But before we start, Lorenzo went through a wormhole, or a wormhole also known as a hallway.
Very good.
Okay, so you should be able to, as soon as I put them on, you should be able to see the notes kind of about now. Okay. So what do you want in your notes?
I think it is, okay.
Like the second page?
I think if you go to the second page, yes. Okay, yeah, here we're talking about the study of Beckenstein. If you go up.
Yes. This here, where you're throwing Ali into a black hole.
Exactly. Here we have the following situation. And here I'm trying to explain why black hole need to have some entropy. 1 second, I mute myself in the other laptop. Okay. The argument of Beckenstein is the following. Let's assume we have one Ali in the universe that is throwing an object, a random object, into a black hole. So maybe, I don't know if any of you is familiar with entropy, with the second law of thermodynamics. Entropy, in a sense, is what people say is a measure of chaos in our system, or like, in a sense, the way our system can rearrange to create the microscopic system. So it's a state of chaos, in a sense. So if we throw this object inside the black holes, the entropy of our universe is decreasing, because we have one object less, in a sense. So we have different ways to create our universe. But the second law of thermodynamics tells us that entropy cannot decrease in a closed system. It must always be greater or equal to 0, the difference in entropy. So that loss in entropy must be somewhere in the universe. And the only place where it can be is this black hole. So in a sense, this very simple argument tells that black holes must have entropy. And this might seem very easy to get, but it's not. Why it's not? Because in general relativity, a black hole is a unique state. There is no entropy of black hole, because there is only one way to create a black hole in general relativity. In general relativity, there is this theorem that is called no-hair theorem that tells that a black hole is uniquely defined once you have a mass for it, a charge for it, and a spin, a rotational moment for the black hole. So once you have these 3 charges, the black hole is uniquely defined. You cannot create a black hole in different ways. So there's no entropy, because you have only one way to create your black hole. And this argument tells that general relativity in this sense is wrong, or else general relativity is not enough to describe all we want for a black hole. It's enough to describe how we move around the black hole, how we can measure or can we see the black hole, but it's not enough to describe its nature. You need something more. You need a thermodynamical or a statistical interpretation of what is a black hole.
Okay, so before we jump into like what else there is and what we need, just want to recap what we're saying here. And I'm still trying to figure out the best setup, and I think it's this with me hidden and you two very visible. So we're going to go for this setup for now. So black holes, regions of space-time that are so dense that not even light can escape. And we've got as far as throwing Ali or an object into a black hole. We want to know what happens to the information and to the entropy. What Lorenzo is saying is that this is something that general relativity by itself is not sufficient in order to answer this question. So to answer the question of what happens when we throw Ali or a chair or something into a black hole, we need something else. And this something else is, you're saying, thermodynamics. Or quantum physics, depends on...
Yeah, there are different ways to address the problem. Like the first attempts was to give a thermodynamical interpretation to the black hole. Now, after 20 years of study, people have tried more difficult approach, like with string theory, quantum gravity, and stuff, which I'm not an expert of. So please don't ask me about string theory explanation of black holes. But yeah, I think thermodynamics is the first attempt to explain this phenomena in the black hole, like this statistical interpretation.
So do we want to explain it from a thermodynamic perspective and then from a quantum perspective, or do you want to jump straight into quantum?
If we have time to do thermodynamics, we can do some of it.
Yeah.
Let's do thermodynamics. Ali, go ahead.
No, I thought that, well, David Howden asked a very good question, and I think this is the question we ultimately are trying to answer. If the information in the black hole eventually comes out, how is the entropy actually lost? So, well, I guess in Lorenzo's beautiful notes, he says that what happens is that at the end, the black hole evaporates. And how the black hole evaporates is that it releases some radiation that carries away its mass with its energy. And the main idea here that I think he presented is that it doesn't matter what the initial state was. So you can throw an apple, you can throw a cherry, you can throw a whatever. Yeah, and then in the end, it just comes out as some radiation, and so the initial state is actually lost. And this is how the entropy is completely lost in. Well, this is how the information is lost in the system, and this is called like the black hole information paradox. I mean, we were supposed to discuss that at the end, but I thought it came up.
Yes.
Yeah. So we're jumping through a lot of topics here. So why are we calling this a paradox? Well, from a quantum perspective, information cannot be destroyed or created in any way. It can only be transformed. So information cannot be destroyed. It has to be preserved somehow. However, if you're throwing an object into a black hole, what we're now saying is that this information is going to be lost somehow or changed in a way that is completely destroying what was there. And this is something that doesn't sit right with people. And because you mentioned evaporation of black holes, I want to make a comment on what you said, because Ali gave a very nice short explanation here about evaporation of black holes. But we need to be aware here that we're not omitting something from the black hole itself, because nothing, not even light, can escape a black hole. So what you're actually doing is you're borrowing energy from the universe to create a particle and an antiparticle. This particle and antiparticle normally will meet again, annihilate, and give back the energy that was borrowed. However, if you produce this particle and antiparticle on the event horizon of a black hole, which is the point of no return, one of them can fall in and the other can go out. So now you've borrowed energy from the universe to create these particles. One has fallen in, one has gone out, but you need to pay back the energy that was borrowed because energy needs to be conserved. And the way you do this is by the black hole losing a bit of mass to compensate for the particle that was created and ejected. But this doesn't mean that something is escaping the black hole itself. Now, if this happens over a long enough period of time, the black hole is gradually going to lose more and more mass and eventually evaporate. And now the big question, what happens to the information or the entropy of the objects that we throw in? This is what Lorenzo is going to try to explain with thermodynamics. But before we do, we have a question from Ben that I knew was going to come up today. What about the correlation between expansion rate of the universe and the mass of supermassive black holes? Could that resolve the GR problem, or is it totally different? So this is a very interesting paper that came out recently that we are not going to discuss today, but the short answer is please do not believe that paper. And I will elaborate on this. It's a very interesting idea. There's a lot of cool stuff in the paper, but it is not the prevailing opinion in the community. Moving that aside, Lorenzo, thermodynamics, black holes.
Yeah, there's also another question by Paul Hess. It says, like, what if a particle escapes and next time the antiparticle escapes? Will that balance out the effect? I think, like, it doesn't matter if it's a particle or antiparticle going in or out. What matters is the energy is going in and out. It doesn't matter the charge of the particle you're considering. It just matters the energy that it carries. And so the information.
Normally we have the idea that particle-antiparticle meet, they annihilate, they produce radiation. But in this sense, they're not necessarily going to meet. They're not necessarily the same type of particle and antiparticle that can annihilate. So there's no reason to assume that it would balance out over time and that these would then annihilate and result in net zero. So each time you're doing this process, you are borrowing energy from the universe, and each time you have to pay it back. Another comment here from Scott about black hole volume and the singularity of the event horizon. Is the singularity volume actually zero? Let's shelve that discussion because that is interesting, and then we're getting into the physics of black holes. But let's go back to thermodynamics of black holes.
It depends from the black hole. For some, yes. For others, no.
Do you want your notes back on screen?
Maybe yes. Can you scroll down?
To here?
Okay, so the argument of Beckenstein was an introductory argument just to say that we need statistical interpretation of black holes. And in the next years, Carter and Hawking derived some laws for black holes, and they found analogies with what we already know from thermodynamics of Newtonian physics. So we are going through these laws one by one. Do you want to explain some?
Yeah, if you do the first one, I can do the one after.
Okay. Here is the zero law of thermodynamics, which says that temperature is constant in a system in thermal equilibrium. This means that if I have a pot of water, for example, in a room temperature, I put a thermometer to measure the temperature of this water, I will see that the temperature is constant. There's no change in temperature. And Hawking Carter found the analog for the black hole that says that the surface gravity, and now I'm going to explain what is the surface gravity. The surface gravity is constant along the horizon, event horizon of a black hole. Can you scroll down, Diana, a little bit? So I think I have a picture again with Ali. What a surprise! There's Ali here that is close to the black hole, close to the event horizon. And here Ali is going to explain what Ali, like the picture Ali is going to explain us what is surface gravity. Basically, surface gravity is the acceleration that you need to stand still on the surface of the event horizon. So basically, what happens when I approach a black hole is that the gravitational attraction wants me to come in, to enter, to go through the singularity. But until the event horizon, I can always escape this attraction. And at the event horizon, the acceleration that I need at the event horizon, I cannot escape fully. I can just stand still at max. And the acceleration that I need to do that is called surface gravity.
So if I can just interject something here, these laws of thermodynamics that Lorenzo and Ali are going to present are not just about black holes. They're general laws of thermodynamics, but we can draw parallels between these laws of thermodynamics and black holes, which is really cool because thermodynamic laws appear in a lot of things. And what we're doing here is trying to explain information lost in black holes using thermodynamics. Go ahead, Ali. Sorry, Lorenzo, whichever one of you is next.
Yes.
Yes. Okay. So if you scroll down, what?
You're on to first law of thermodynamics.
Yes. So in the first law of thermodynamics, we know that the total energy of the system is conserved. So if you have any system, there are these thermodynamic laws that tell you that the total entropy. I think what you are writing here is that the total energy is the entropy plus charge plus.
Yeah, here, like the variation of the total energy in a fluid dynamic system is equal to the variation in its entropy, in its charge, and its rotational moment. And this variation has to amount to zero in a closed system because energy is conserved.
Yeah, so that in a closed system, I think this is key. So if you are accounting for all of the interactions that are happening, then the total energy within your system is always conserved, and it's given by these three things that we wrote down. So, for example, an ice cube melting, like what he drew here, it absorbs heat, but then it increases volume, and if you use down the thermodynamic equations, at the end of the day, the total energy is conserved. Whatever energy the blocks have absorbed from the surrounding to melt, the ice blocks have absorbed from the surrounding whilst they're melting, is always conserved in this interaction.
I think another example we can use, which to me always helped understand this thing, is the idea of a piece of wood that you can set on fire. Initially, you have the wood, and this has a certain amount of potential energy, so the energy that it could generate if you burn it. And then if you set it on fire, at the end, you're just going to produce the fire, the heat, and you're going to be left with ashes and smoke. And it might look like these are very distinct things, but the overall entropy, the overall energy of the system is conserved. Sorry, not the entropy, but the overall energy of the system is conserved, because you've gone from having it in one state where it had a lot of potential and was, in the wood configuration, to ashes and smoke. But you released a lot of energy with the fire that you produced, so the overall energy is still conserved. And I see we have a few questions here and an off-tangent comment about Carnot and mitochondria. So everything we're talking about so far, are we talking about spinning or non-spinning black holes?
These things, they, like the law of thermodynamics or black hole mechanics, they hold for any kind of black hole. But I think the most interesting black holes are the spinning ones, since they are the only, like, static black holes, like the Schwarzschild black hole, are not astrophysically viable. I think only spinning black holes are real in a sense. And also, a lot of processes that we will see later are motivated by spinning black holes and not by static black holes. But so far, what we said so far holds for any of them.
Yeah, and there's the cool question we can ask there: why are black holes spinning and not static? And the answer is because almost everything in the universe spins, because it's very easy to give something a bit of a push and get it spinning. It's very hard to have something that is completely not spinning in any way. People in the comments have just pointed out that, in fact, ice has more volume than water, which is actually true.
Yeah.
So I think we slightly misspoke with that, but it's good that people are aware and calling us out on these things. But yes, we do need to consider the overall volume, the entropy, the change in structure.
Yeah. No, and I wanted to make a quick comment also on why most black holes are spinning. Is that even if an object is let's say a star, is somehow managed to not be spinning.
A what, sorry?
If there is an object that is somehow not spinning, if it is collapsing towards a black hole, in the same effect that, well, when you are spinning around like yourself and you bring down your arms, you can spin a little bit faster because of the conservation of angular momentum. If there is a very small perturbation that gives any small push in the beginning to this star, if it has the smallest bit of angular momentum, as it collapses to the black hole, I'm guessing, the black hole would rotate a lot faster than the original star.
Yeah, so Scott is adding here that most of the time people talk about non-spinning black holes, and the reason is because the equations are simpler. We like simple things, so we always start with the non-rotating black hole as a good proof. Like, hey, look, we know how to solve it in the easy case. So yeah, if you've heard talks or read anything about non-spinning black holes, it's because it's easier to deal with. But realistically, we want our black holes to spin.
Yeah, I guess the generalization is not that hard. It doesn't add too many things. So once you understand the static black holes, it's easy to generalize. So it's a good start.
Easier. Yes, it's a good start. Okay, so we have zero law of thermodynamics. The system, if you don't do anything to it, it's going to stay the way it is. We have first law of thermodynamics, energy. We wanted to relate first law of thermodynamics to black holes, right?
Yes. So if you can put up the notes again, yeah. So in the case of black holes, the analogy here, the analogy is that the total mass is conserved for the black hole. So the total mass is given by this combination again of area, charge, and rotational moment. That
here area is a bit generic. What I mean with area is the volume area of the event horizon, which you can exchange for the mass. They are related. Basically, like the variation of the total mass is related to the variation in the area of the black hole, and the variation of its charge and its spin with angular momentum. So this conservation of energy, they match in the black hole case and in the thermodynamic in a normal fluid system. And here you already see that this hint that area, in a sense, is related to entropy. Because if you do the comparison with what we said before, you have a one-to-one correspondence between this conservation of energy, and in particular, you have this one-to-one correspondence between area and entropy. We are not going to show the calculation for this analogy, but we are going to use it later, probably. Okay, yes, let's go fast to the last.
But before we jump into the most fun thermodynamic law, we have questions here about how are we discussing charged black holes? Does anything change if we make our black holes have charge? And does adding a spin to a black hole change the size of the event horizon?
So adding the spin causes all kinds of really interesting effects that we aim to discuss, hopefully. At some point.
But yeah, the answer is yes. In both cases, both the charge and the spin vary the size of the event horizon. But yeah, I don't think it's very useful to know this relationship. I mean, you need to have the metric of a black hole in mind. But yeah, the answer is yes to both cases.
Mm-hmm.
But for now, for simplicity, let's assume a non-spinning, non-charged black hole. Try to apply thermodynamics to black holes, and later on we'll try to make things more complicated. Okay, who's covering the second law of thermodynamics?
Yeah, I'm gonna talk about that. This is quite easy and quite cool. Second law of thermodynamics tells that yes, it tells that the entropy cannot decrease in a closed system. This is easy to see, to visualize. For example, in this pool table that I draw, I don't know if it's clear that it's a pool table, but here you have in the left you have these, all the balls are organized, and the first kick is to basically destroy this configuration, and it's easy to go from left to right. In left, you have this organized configuration. In the right, you have this disorganized configuration. But it's impossible, or at least it's difficult with, let's say, with one kick to do the inverse, to restore the configuration that we had before. So this is a way of saying that, again, chaos, as I guess people used to say, has only one direction. That is the direction of increasing of entropy, increasing of chaos. People sometimes also talks about time being irreversible, but that's probably a more philosophical question.
Yeah, you can tie in time with entropy, because if I drop my mug on the floor, there's going to be two states. There's the mug now with tea, and there's the broken mug on the floor. There's clearly one state with more entropy, one state that is more ordered, which is this one, and one state which is more chaotic, which is the broken one. And there's thousands of different ways I can drop this mug and break it, but there's no way that the broken pieces are going to reassemble into a mug. This gives us an arrow of time, an event A that leads to an event B. And also entropy is the reason, if you've ever wondered why when you put your headphones down and then pick it up again, the cable is tied up. It's because there's billions of ways the cables can be tied up and only one nice ordered one. So anytime you pull a cable out of your pocket and it's tangled up, you can blame entropy.
Yeah, I think Paul has asked a very good question here.
Yeah, I can stress this thing. Tends to increase is a bit generic, cannot decrease is not so strong as it might seem. In the sense, cannot decrease means that the variation in entropy cannot be negative, but it can be zero.
Yeah.
So you can have transformations where entropy doesn't change. So it's not decreasing, it's not increasing, it just stays constant. The thing is that it cannot be negative. So tend to increase is of course correct, because entropy can increase. Tend is a bit generic. Saying cannot decrease, I think, is for sure good. You just say what you cannot do. But
yeah, and I think really well, I was discussing that you take into account the full system. So, for example, a refrigerator can decrease the temperature and therefore entropy inside, but always at the expense of,
yes.
of causing something outside of it to have even more entropy.
Yes.
So again, once you take into account the entire system and you take into account everything, then these laws hold. So yeah, do you want to finish the analogy to the black hole?
Let's throw this at black holes.
The black hole analog is that the area of a black hole cannot decrease. So if I throw Ali, or Ali's planet in this case, into a black hole, there's no way I can make the area of the well, here there's some subtleties that maybe we can discuss later, but let's say in the general picture, there's no way I can make the area of the event horizon of the black hole decrease. The area will always increase. So here again, we see this analogy between this one-to-one correspondence between the area of the event horizon and the entropy.
Okay, so we've got 3 laws of thermodynamics. We've just applied them to black holes. There's a bunch of very cool questions, people going off in very cool tangents, like, how can a black hole be charged? And other people in the comments have proposed get a bunch of electrons, squeeze them together. Theoretically, you can make a black hole, or photons. There's a lot of ways you can make a black hole that has charge. Photons are indeed not charged, but you could end up with a fun Kugelblitz-style black hole. But let's shelve all of that. There was also a very interesting question about what happens to the mass of if the singularity is infinite, and I want to answer that one, but not right now. So 3 laws of thermodynamics, we've applied them to black holes. Does this answer the question that we're trying to answer here of what happens if you throw something, Coralie, into a black hole? So where are we with that question? We're trying to answer the question of what happens if we throw something into a black hole, right? You said let's use thermodynamics, so we've done that. Do we have an answer to our question?
Well, I think the question was badly stated. I think like the main point of this discussion is what we can do with this thermodynamic interpretation of a black hole, and the answer is that we can show that black hole emit something. They are not all black, as we might think, which I think is the main result from this statistical interpretation of black holes. Then what happens if we fall into a black hole? There are many possible answers, because of course, it always depends on the kind of black hole that we have. Maybe we can have fun with that.
Okay, so before we spend too long on the thermodynamics, which is very cool, just to recap here, the idea is that when people were initially thinking of black holes, they were trying to understand what happens to information that goes into a black hole.
Yes.
A way of understanding this was proposed using the laws of thermodynamics. If you apply the laws, as Lily and Lorenzo just explained, you reach the conclusion that in order to preserve entropy, a black hole must emit something, or some way the information must escape in some means. And this is what we know today as Hawking radiation, which is this idea that we mentioned before of particles being produced on the horizon and carrying away some information. However, there is still the big problem here that the information that the particles carry away is not necessarily the same as the information that gets thrown in. As we were saying, you can throw in a chair and then emit a particle. So we still have the problem with the information here. And this is still known as the information paradox. There are different ways you can try to solve this. One of them is throwing in quantum physics, which is fun, because when you get down to the ideals of singularity, we need quantum physics because we're moving to the very small world. I'm just going to take this chance to say what we mean by, because we're throwing around the word singularity here. And a singularity is a fancy way of saying our equations stop making sense. So when we talk about the singularity that is a black hole, it's not a physical concept. It's not a physical quantity. It's just the mathematical description that breaks down. So an event horizon is a type of singularity in the sense that at that point our equations stop working, but what we do to get around that is just change how we phrase our equations. So there was the question of what happens to the mass of a black hole if the singularity is infinite. And an infinite singularity is... Sorry, say that again?
What happens to the mass of the black hole if the singularity is infinite?
Exactly, yes.
An extension.
Yes.
Hmm.
Yeah, so because the singularity itself is more of a mathematical description and a mathematical statement of, we're not sure what happens, then it doesn't matter. You still have an object that has a lot of mass, and it's just very hard to describe mathematically. And this is why we try to throw quantum physics at it as well, also to explain this whole information question. And here we can get into the very cool idea that I'm not sure if the guys wanted to discuss today, which is holography, and the idea that all of the information of a black hole could be encoded on the surface of a black hole. This is a very cool idea, and I think we're going to leave it at that. So we did a whole stream on holography with Oscar Henning, someone else from the group, quite some months ago, and I don't think any of us three want to get into holography, but you can have the idea that you encode all of the information of a black hole on the surface. Okay, so people in the comments are asking here, we've thrown Ali or Ali's planet into a black hole. Can we ever recover this information? Let's say we've thrown Ali into a black hole. Can we get an Ali back at any point?
Okay, I guess this has nothing to do with, or maybe, I don't think it has to do with radiation of black hole or with thermodynamics of black hole. I think the answer is no, in any case. For every black hole, we cannot have that information back. But it's possible that the information reaches other patches of the universe that are not causally connected with us, with our universe, if that makes sense for people. It's a bit of a flip here. If you have a spinning black hole, so you have two horizons. You don't have one, you have two event horizons. And going through the first event horizon, you're forced to go through the second event horizon. So you basically enter, you pass through an event horizon twice, and you go out in a region of the universe that is as ours, just you're close to the singularity, so you're close to death in a sense. But inside that region, you are always able to escape. You're always able to re-enter, going outward to the inner event horizon, and then once you enter from the other direction inside the inner horizon, you are forced to go out through the second horizon and, in a sense, re-exit to the normal world. But the normal world is not our world; is another universe that is conformal to ours, in a sense that there are the same laws of physics governing that universe, but this universe is not causally connected to ours. So we will never meet again, in a sense. We will never see each other again. We will never see Ali again, poor Ali.
Just want to add that
it's possible to go in and to go out and survive.
So just want to add that all of this is hypothetical.
Hypothetical.
Yes, this is very hypothetical.
For theoretical physicists, is sure.
Well. So if you throw something into a black hole, we have no idea what happens beyond the event horizon because our math breaks down beyond the event horizon. It's very, very unlikely that you're going to reappear in a library like in Interstellar. But what Lorenzo's getting at here is if you have a spinning black hole, then the event horizon, it has a different meaning because you kind of have an event horizon that is being dragged around in what we call a Penrose process. So this is going to lead to what appears to be an event horizon, not, and then someone who falls into the black hole from our perspective actually hasn't fallen in because of the event horizon situation that you have here being dragged around. Now, we're not in any way saying that you can use black holes to travel to another universe. I want to add this disclaimer here because while it's very fun to think about, we are in no way saying jump into a black hole to travel the universe. Your takeaway from this should actually be please don't throw your friends into black holes because you will never see them again.
Yes.
Someone's made a comment here, Vali will know whether that's true, but we won't. And now I want to take this chance and throw it around of what would you feel if you were falling into a black hole? Would you know that you've crossed the event horizon? What would you see? Again, this is hypothetical this is where we get to have fun because we can't actually prove any of this. So what do you two think would happen if you jumped into a black hole or if your friends threw you into a black hole?
Well, okay, a few years ago.
I fell into a black hole.
No, a few years ago, there was this suggestion in the scientific literature called the firewall, wherein an infalling observer would encounter a firewall and just somehow spontaneously burn up.
I think it's the Unruh effect.
I don't think that's the same thing. I think the firewall was suggested by a different person, so probably it's not the one.
Okay.
but now this is no longer, I think, widely accepted. But now I think it is, and it has gone back to what was always, for a while, what had always been said about an infalling observer to the black hole, that he wouldn't see anything necessarily other than the fact of spaghettification due to tidal forces. But if you ignore the spaghettification, they wouldn't even be able to tell that they have fallen into a black hole, or at least that's how I understand it.
So you just threw out the word spaghettification, so now I have to ask you to explain what is spaghettification.
Do you want to explain spaghettification?
Spaghettification is, I think, is
Let's
just
get
a
the
title.
Italian to explain.
What?
Let's get the Italian to explain spaghettification.
Spaghettification, you put the X. No, spaghettification is just a tidal effect of gravitational interaction, gravitational attraction. Basically, if you imagine to fall with your head pointing radially toward the singularity, and your feet are behind you, so you're entering like a swimmer. The tidal effect is like the gravitational force that is in your head is way higher than the gravitational force that is applied to your feet. And so basically you get elongated, you get stretched because your head feels more force than your feet. So basically you get this stretching, and okay, I guess you cannot survive long. I don't know, I never did a calculation of how long can your muscle stand.
I did at some point. It is not a fun calculation to do, but you can calculate. There are precedents for seeing how much a human can survive in terms of being stretched, right? There are nasty precedents there. And you can actually calculate how long a human would survive jumping into a black hole. If one wants to do that calculation, one can. But yes, it's not a calculation we do often.
Yeah.
Yeah, so it's basically tidal effects, like tidal forces, the forces that cause these tidal effects on seawater, but it's taken to the extreme that well, yeah.
Right, so currently we have, if you jump into a black hole, I just lost it at the Ali Carbonara comment.
No, because Silvano, this is my friend.
Okay, so we've thrown Ali into a black hole from...
Oh no.
Okay, calling Lorenzo French is a good way to upset people on the stream.
It's not the first time.
It's not the first time, and I think it's the same person.
I think you deserve.
Okay, yeah, so we've thrown Ali into a black hole head first. Ali has been spaghettified, but assuming you survive the spaghettification, you will not actually notice that you've fallen into a black hole, because there's no thing that you hit that suddenly you've hit an event horizon. Some people, as Ali was saying, used to think this idea that you have kind of a firewall where suddenly your light is falling in with you. It's not clear if that would happen. So if you're falling head first, you might not realize that you've passed the event horizon. And then we have the cool thing that we have time dilation effects, which means that for you, time would still be ticking normally, but somebody outside would actually never see you fall into a black hole. So let's say Lorenzo's thrown Ali into a black hole and is sitting back to watch with satisfaction. You will never actually get the satisfaction of seeing Ali fall into the black hole, because from your perspective, time and lengths are going to contract and change so much that it will look like Ali just stopped on the event horizon at some point. From Ali's perspective, everything goes on as usual. You survive spaghettification somehow. You're just cruising in the universe. But from an outsider's perspective, you are frozen on the surface, on the event horizon of the black hole.
I think this is all if I'm already a spaghetti. So
sure.
This is all if there is no spaghettification. So
yes, we're assuming that spaghettification is not an issue we need to worry about here. There's too much Italian food influence in astrophysics with spaghettification and neutronium pasta. There are a type of galaxies called pancake galaxies, so that's not, you can add that one in. But yeah, I think it's just because we like Italian food in general, and we like bastardizing Italian food and putting pineapple on pizza.
Pancakes are Italian?
No, pancakes are not Italian. I'm sorry, Lorenzo, you don't get to claim pancakes.
It's okay. It's okay. We have some.
I appreciate the Hotel California reference in the comments. I remember seeing a show like 30 years ago based on Hawking's work that said as you fell into a black hole, you wouldn't witness the end of the universe due to time dilation. Exactly. From your perspective, things are going as usual, but everything outside is going to change very, very, very drastically.
Just a historical note. Black holes at the beginning were called freezing stars or something like that because of this time dilation effect. Because like, if you imagine the black hole coming from a star collapsing, from outside you will never see the black hole forming because you will always get freezed at the moment you have this time dilation effect. So you will never come to the point when you see the light entering the event horizon because it will freeze the moment it goes to the event horizon.
So the image freezes and then it redshifts and just gets more and more fades away until it just casually and slowly disappears in infinite time. But it never actually just you never actually see what happens on the inside. And I suppose this is what we call that you lose causal contact with whatever is inside. And I suppose this is what that comment meant, that whoever is inside the black hole has no causal contact with anybody outside. They can no longer communicate. So yeah, if the world ends, it's not their problem.
We have a very nice question here from Ben about, is there a relationship between a black hole singularity and its event horizon, or are they independent? Do we think there actually is a singularity? Love this question. And it goes back to what do you mean by singularity? And if we take singularity to mean the point where our equations break down, which is a very mathematical description, there are actually two singularities within a black hole. There's one right at the center. We have no idea what happens at the center, and this is what is often referred to as the singularity of the black hole. It's a point with infinite energy, infinite density. It's not really, it's just a point where all of our equations explode. And this one is a physical singularity. We don't know what to do with this one. And then there's a second one, which is a mathematical singularity, which is the event horizon itself. And the reason I say this is a mathematical one, because if you do your general calculation of a black hole and you calculate this event horizon, the point of no return, you find that your equations do funny things. But you can change how you express your equations. You can do what we call a coordinate change, where you move and put yourself within the frame of the black hole. And then the description of this event horizon disappears. So the singularity itself here is a mathematical one. And this is what we mean when we say also if you fall into a black hole, you're not suddenly going to feel that you're hitting the event horizon, because physically there's nothing there. It's just a mathematical description. However, the singularity at the center of a black hole is something that we think is different, because it's something that whatever you do, it's still there. So singularities are very much a mathematical description, but we can make the distinction between avoidable and unavoidable ones. Do you two want to add anything to my singularities ramble?
Something to add to this is that, like, for example, in a Schwarzschild static black hole, the singularity is a point. That is, I'm going to use a very technical word. It's called time-like point, in the sense that you cannot avoid reaching that point once you enter the horizon. If you have other topologies, like if you have a spinning horizon, topology is a bit weird. If you have other configurations, like a spinning horizon, spinning black holes, then your singularity has a different shape. It's not more a point, it's a ring. And that ring is space-like, in the sense that you can always dodge the singularity through an appropriate path. You can dodge the singularities. And this is the same for a charged black hole. In this case, the singularity is not a ring, it's not a point, but it's a line. And it's again space-like, so you can always dodge the singularity.
Well, speaking of dodging singularities in a spinning black hole, I think this is a good digression to speak about the Penrose process. So, well, we can try to do it together. So,
I mean, we already did somewhat.
No,
right?
we can speak about this very quickly. So if you have a spinning black hole that is spinning fast enough, you get this pumpkin-shaped region outside of the black hole. Well, an object falling in. Yes. Okay. Yes. So an object falling in can, if you go down a little bit. Well, yeah, here. So let's say that this is the pumpkin-shaped or egg-shaped region outside outside the spinning black hole, and you have one particle falling in along this path from down to up.
You should explain what is an ergosphere.
What is
the ergosphere?
No, we don't have to. Okay.
Just pretend you don't have the word ergosphere written down and move on with it.
Yeah. So do you want to explain what happens here to this path of this particle as it enters?
Yeah. First, I'm gonna explain what is drawn there. This black circle is the event horizon of our black hole, and the blue egg shape, the blue rugby ball shape, is what people call ergosphere. Ergosphere is not an event horizon, but is a region inside which observers or ALIs cannot stand still. They are forced to rotate with a spinning black hole. The spinning black hole basically is dragging the space-time around it, and an observer that is inside this blue region is forced to spin along with the space-time that is dragged by this spinning black hole, and this is called ergosphere. So here we have let's say a particle, an object that I call P with a lot of fantasy. This P is entering the ergosphere, and at some point it breaks down. It splits in two particles. Particle is called P1 and particle is called P2. P1 is going out of the ergosphere because let me stress this fact: like inside the ergosphere, you are forced to rotate with the spacetime, but you're not forced to fall in radially. You can always escape as long as you are outside the event horizon. So P1 is going out and P2 is going in. I don't know. Do you want to continue?
Yeah. So I guess the point here is that the point falls into the special region and it breaks into 2-point particles. One of them falls into the black hole, and the other can now escape with even faster energy than when it came in. And so it extracts energy from the black hole, and it extracts angular momentum from the black hole and mass from the black hole.
Yes, like the cool thing about this phenomena is that you have a particle P that is going in with a certain energy and a particle P1 that is going out with another energy. And you might think, conservation of energy tells me that P1 must have less energy than P because there's some energy contained in P2, so energy must be conserved. Well, this is not the case. There are situations where you can have this particle P1 going out with greater energy than P. And this is why we say that you can extract energy from the black hole. This is called Penrose process. And the way this happens is because P2 can fall in the black hole with negative energy. And okay, now I guess explaining why you can have negative energy might be a bit technical.
Yeah, you can't just throw out negative energy without an explanation.
5 minutes before the stream, but I mean, okay.
Okay, what is negative energy? What are we doing here?
I think this, like the Penrose process, is just a process that explains you that you can extract energy from the black hole. So in principle, you can solve the energetic crisis in the world using black holes. Because
again, hypothetical. We have never confirmed that Penrose processes exist.
This is all a very highly hypothetical.
Yeah, no, the thing is we're mixing things here, right? Because spaghettification is something that should happen. If we're talking about Penrose process and saying it could solve the energy crisis, let's be clear that this is hypothetical. We've never actually measured a Penrose process happening. Hypothetically, you could harness the power of black holes.
Sorry?
Hypothetically, you could harness the power of black holes if this is true. But we have no idea how we would harness that or how to do it or if it's even true.
Yeah, I want to say hi to David.
We have a lot of Davids in the comments.
Well, yeah, he's okay.
Yes, I gather you saying hello to the one who just said hello to you.
First There was a question that I liked. I don't remember who texted the question, but they say like if you have a supermassive black hole, spaghettification might vanish or not happen.
Yes.
I think that's correct in a sense that spaghettification works because you have a huge, big gradient in the gravitational force. If you have a supermassive black hole and you are close to the supermassive black hole, you have a super strong gravitational interaction, but the gradient of the gravitational interaction is little. So the smaller is the black hole, the better in a sense for spaghettification, or the worse for Ali.
Also, if you don't dive head in, but if you try to fall like just horizontal, vertically into the black hole, I think that might help also.
Yeah. You know, like when you jump into a pool and you're told you should dive. Here, don't dive. You want to fall on your belly into the black hole.
Exactly. You want to belly flop.
Going back to the idea of throwing Ali into a black hole, we had the question from Paul before. If Ali had very, very good instruments and was very smart, which Ali is, would you be able to feel that you've gone beyond the event horizon? So would you have any way of knowing that you've crossed the event horizon if you had any tool at your disposal? What do you think?
I think I would just suddenly see the rest of the world going out of causal contact. So I would see the rest of the world kind of dimming and being redshifted. So maybe that's a red flag for me. But there is nothing really that I can do to establish this, I think.
So actually, I'm going to throw a question at you, but before I do, because it's a question that we will probably wrap up on, is there anything else you wanted to say about Penrose processes, other than hypothetical could harness the power of a black hole?
I think the Penrose process was useful to understand Hawking radiation, because it's like Hawking radiation happens with the Penrose process, when instead of a particle going in, you have a production of particle-antiparticle on the border of the event horizon.
I didn't know that.
That is cool. Yes.
Yeah.
But
yeah, like we probably skipped things.
Sorry. Yeah, if I knew, I wouldn't have said before. But I didn't relate, I guess, Penrose processes to Hawking radiations. But yeah.
Someone is asking the very valid question of why are we always throwing Ali into a black hole? And the answer is you can't throw me in because then the stream would end. Lorenzo is the one who wrote the note, so Lorenzo gets to throw Ali into a black hole.
I think he didn't mean it, but it looked like that, right?
What?
Like in the notes, you didn't mean to write, because he wrote Ali, and I think he means me as an observer, and then there is an object next to me. But yes. I think it can also be easily understood as Ali is the random object that we must throw into the
Yes, I absolutely understood this as we're throwing Ali into a black hole.
Yes, he means I am the observer.
But yes, that's definitely not how that came across. Okay, so Penrose process is really cool. Hawking evaporation, really cool. Thermodynamics applied to black holes, super fun. We've covered spaghettification, Hawking evaporation. We've covered a bunch of things. And I want to ask a question that we actually set our students when I was teaching when I was the teaching assistant in general relativity in Aachen. It was a very fun question until I had to calculate it myself. So imagine you're a stormtrooper, or somebody who has one of the typical sci-fi laser pistols, and you get thrown into a black hole. So you have your nice laser pistol from sci-fi, your pew-pew gun, you get thrown into a black hole, and you're falling in backwards. So you're falling into a black hole, and as you're falling, you shoot 3 shots on your laser pistol. One of them before the event horizon, one of them at the event horizon, and one of them after going into the event horizon. What happens to the laser beams that you've shot in each of these cases? And this was an exam question that the students had to calculate, and I'm asking you to do it without calculating. Just what do you think intuitively would happen?
Question for me? For Ali?
For both of you.
For the event horizon, the light escape.
Right, so you're falling into a black hole. The one that you fire before the event horizon is going to escape, right?
The one that you throw at the event horizon is going to stand still. It's going to stay there.
Okay.
The one that you throw when you are inside is going to punch your head. It's going to...
And go inwards. Right, so...
You shoot, and it hits you.
Yeah, because it's being attracted to the center.
Yes.
Right. So then you could ask the question, going back to the idea here of could Ali figure out that he's crossed the event horizon? If you continuously shoot your laser beams, when you're outside of the event horizon, you see it moving away from you. At the event horizon, you will see it standing still. And once you're in the event horizon, it will fall towards you. Now, of course, this doesn't technically work because there are no photons reaching your eyes at that point because of the event horizon. But theoretically, you could use a continuously emitted beam to see where you are in relation to the event horizon. What do you two think? Is this reasonable? This was an exam question. I did preface with it. We're not going to figure it out completely.
Well, what is the question? Sorry, because I'm reading the comment. Because it's too fun.
Do you agree that we could use a laser beam to figure out if we've crossed the event horizon? What is wrong with this argument?
I think you can realize if you're inside the event horizon.
By the laser beam. So then there's...
I think no. To me,
no,
I'm sorry,
because...
but I don't like it.
Why not?
Because you're falling in faster than the light. So the light never reaches you.
No, because locally, locally speaking, you never see any gravitational effects. Gravity is always a distant thing. So for any local observer, this is all with respect to an outside observer. But I feel like with respect to somebody inside, you should not see. You can only see tidal forces, but you cannot see gravitational effects.
Excellent. I love that answer, and that is the answer I was going for. Yes. So you passed the exam. Well done. So your RTR exams were very reasonable.
Because right now I am the teaching assistant for general relativity here. So if I don't get it right, then Aachen has something in Helsinki. So
yeah. So again, we can go back to what we were saying before, that the event horizon of a black hole is not a physical singularity. It's one that is just a mathematical description. So an outside observer watching this stormtrooper shoot the gun will see the light beams behave differently, and obviously won't see what happens to the one beyond the event horizon. So if I'm watching this stormtrooper fall into the black hole, shooting the laser pistol, I'll see the one shot from outside the event horizon. The one at the event horizon, I'll see as standing still, and I won't see the one afterwards. But the stormtrooper will not see any difference. They will always see the light beams traveling away from them, because they will not physically have noticed the effects of falling into a black hole. Do you both agree with this now?
Yes. I mean, all of these effects are always relevant to an observer. Something happening far away, relevant to an observer. So this is why I guess Lorenzo was always drawing me and then the object, although that didn't come across. But this is why you always need an observer. You always have to think whether you're observing things from, because that always makes a big difference.
So I like that Paul already called this in the comments and said it was a trick question. People are saying that the stormtrooper would miss, and yes, absolutely. So I like that people are engaging here. You can't see the lasers, we can only see reflected light. Nice. I don't think the laser shot inside the horizon would just follow you without hitting you. Okay, so I like that you all discussed this, and I'm sorry for throwing a trick question at you two like that, but well done, Ali, you figured out my trick question. Which is good, right? Because, as you said, you are the teaching assistant on this course. So now you can ask this question to the students and get them to calculate exactly what happens, because it's a very fun calculation to do. Like, you can calculate the trajectory of the light beams. Yeah. And someone is pointing out that the speed of light is constant to any observer. Absolutely. Regardless of what you're doing, light will always travel away from you at the same speed of light. So when I said the stormtrooper sees the light standing still, that should have been a red flag to everyone.
Yeah, I was thinking.
Yeah,
no,
and also
relative to an outside observer, you can see, I guess, here the stormtrooper traveling at the speed of light, or very close to it, near the event horizon.
Yes. Yes, you have a nice time dilation effect. This is like asking about traveling in a car at light speed and turning on your headlights. Yes, it's fun. It's fun if the students have to do the work, less fun if you have to do it. Yeah, when we set this question in the exam, I saw it and was like, this is so cool. And then I was told, you're making the model solution for this. I was like, wait, what now? No. But it is a very fun question, and it stuck with me as a good way to explain that all of these gravitational effects depend very much on who is doing the observation. Because one key thing about general relativity is that it's relative, and it depends on what you're doing and where you're looking from. Okay, so we've covered quite a few things. We haven't covered things like wormholes and time dilation in more detail. We've covered a few things briefly. Is there anything else that you two really, really want to cover before we wrap up?
Me is okay.
Yeah, I guess okay. Or
No,
nothing prepared, at least.
no, nothing pending. Do you two have any open questions after this?
I can explain why there are no charged black holes in the universe.
Excellent. Now, before we get to that, someone had a question before when you two were talking about pumpkin-shaped things, even though I have no idea why you said pumpkin when it was clearly an egg. Someone asked
It looks like a pumpkin. Where did I get this idea?
Someone's asked if we have pumpkin pasta in Europe, and I've never heard of pumpkin pasta.
Yeah, we have pumpkin pasta.
Really? I've never tried pumpkin pasta.
It's good pumpkin pasta. Yes, yeah.
Okay. I thought you were going to get upset, but apparently it's Italian approved. So nice. So we have people asking us to do a part 2 of this some other day. Would you two be up for a part 2 on this? I'm pretty sure Ali would be.
Ali has to drag me.
Can be arranged. So we're up for a part 2 at some point, potentially. Given that it took us 5 weeks to prepare for this one, well, I hope you two didn't spend 5 weeks preparing for this one, but Paul is asking if your notes can be shared, Lorenzo, if we can distribute your notes.
They're not very well written. I mean, I wrote them very in a rush. It's written like ice is losing volume.
So with disclaimers, they can be made available. I will figure out how to host them, how to link them, and I will add them to the comments down below once.
I can make also them better and put some references.
We're not giving you more homework here, Lorenzo.
Okay.
Okay, so you wanted to answer the question of charged black holes.
Yeah, like the reason why there are no charged black holes in the universe is because like the demonstration is by, I don't know how to say this in English, but like let's assume that they exist. If they exist, quantum field theory tells you that in the vacuum, like let's assume that, for example, there is one of these charged black holes in the universe, and around this there is vacuum. The theory of quantum field theory tells you that vacuum is not really vacuum, but is a sum of creation of particles, antiparticles, that in the end they average out and then create this ground state that is not empty state. So you have continuous creation and annihilation of pair particles, antiparticles, which forms your ground state, your empty universe. If you imagine this happening close to your charged black hole, you know that like particle antiparticles are exactly the same particle. They just differ in their charge because they have opposite charge. So let's imagine that your black hole is positively charged. So if this creation of particles happen close to this black hole, the negative, let's say an electron, this negative charge electron will be attracted to the black hole. So there is negative charge electron will be attracted to the black hole, making it a bit less charged, while the positive antiparticle of the electron will be spread outside because of the electromagnetic interaction, will be sent outside. So if you imagine this happening many times, with the time, the charged black hole will be neutralized in time because of this continuous creation and annihilation of particle antiparticles. Because every time a pair is created, the negative couple will be attached to the black hole and the positive one will be sent away. So by the time this black hole will be neutral. So the idea of charged black holes cannot exist in the universe is not that they cannot be created. They can be created, but they will be neutralized in time. And I guess you can calculate the time. The time is not so large because of how frequently this pair is created. This pair particle-antiparticle is created. Also, this is a cool thing that one can do to demonstrate that gravitational interaction is weaker than electric interaction. because you know, like when the particle enters the black hole, you are also creating the mass. This is a bit of a tricky aspect. Like if you enter the black hole with negative energy, so you decrease the mass and you decrease the charge. But if you decrease the mass faster than you decrease the charge, then you basically annihilate the black hole because you annihilate his charge, and this cannot happen. So this tells you that the electric charge must be bigger than the massive charge. So it's a way of saying that gravitational interaction is weaker than electric interaction. So there are
for a much more everyday application of proving that the electromagnetic force is a lot stronger than the gravitational one. You can use a magnet to pick up a paperclip. You are beating the gravitational pull of the whole planet with a simple fridge magnet.
But this is cooler.
This has black holes.
This has black holes.
Black holes are cooler, but less everyday life. Okay, so
they are carbon neutral.
And yes. Okay, so well, they probably have carbon in them, right? Anyway, let's not go there. So I want to wrap up on one question. We've gone over the hour mark. People in the comments are saying we definitely need to do a part two.
Hawking radiation neutralizes the charge of a black. Like Hawking radiation doesn't need to be charged. It can also be neutral. You don't need radiation to be charged. There's a question like Hawking radiation neutralizes the charge of a black hole.
Yes.
But radiation doesn't need to have a charge.
So it doesn't have to be the Hawking radiation that neutralizes the charge of a black hole, just the existence of a charged black hole will over time neutralize it. Okay, so I know there's more follow-up questions and we could spend a long time discussing this, but I want to finish on a question to you two. Of everything we've discussed and maybe things we haven't discussed, what is your favorite aspect or quirk or creative thing you can do with general relativity?
Time travel.
Okay, you can't just throw out time travel at the end without adding the disclaimer of hypothetical. Okay, time travel with general relativity, hypothetical.
Hypothetical time travel is the coolest thing about black holes.
Okay, that's left for part two. Lorenzo, what's yours?
I don't know. I enjoy throwing alleys into black holes.
Okay, time travel, throwing your friends into black holes. My personal favorite thing about general relativity is the production of gravitational waves, which are amazing ripples in the fabric of space-time. We've already found ones from smashing black holes. We might find the ripples produced by the universe itself in a few years. It's not going to take that long. That is very, very cool. And we also didn't cover that today. So for part two, we have hypothetical time travel. We have wormholes. We have gravitational waves. We didn't even get into talking about GPS. And I think I wrote down in the description that we'd explain why you need DR when dealing with GPS satellites. So we're going to leave that for the future. Got a comment here that Lorenzo and Ali are the best double act ever. Absolutely agree. They are very much chaotic in the office, but very fun to have both of them around together.
Yeah.
Okay.
Co-worker also asked if an electron-positron pair appears at the event horizon of a chargeless black hole, you can basically give charge to a black hole. I guess yes, but this would average out because of this continuous creation of particle-antiparticle. So in the end, you are averaging out this effect, and you are not creating a effectively sufficiently charged black hole in a sense.
Okay.
Sorry, it was
no, it's a good thing to do.
Question unanswered.
The problem with trying to answer all the questions is people will keep us here all night if we try to do that. And you two should get home from the office, because I object to you being in the office on a Sunday, but I appreciate you going there for the stream. And hopefully you're not doing work and just there for the stream. So thank you both for joining. This has been really, really fun. Is there anything you want to throw out to the audience before we wrap up completely? You can push your own social media, promote yourself, whatever, anything you want to throw out.
We'll be back.
No, I wanted to thank Diana and thank everybody for having us. It's really a lot of fun.
Yeah, thanks.
No, I was happy ending on Lorenzo's nice note there, we'll be back. So thank you everyone for joining. This has been really, really fun. Cup of Cosmology will be back online Sunday next week, same time as today. That's 7 p.m. if you're in Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. There's a time zone converter on cupofcosmology.com. As always, feel free to reach out by email. If you're one of the 3 people who have been waiting for an email from me for 1 month, I apologize. Emails will come this week, maybe. Thank you everyone for joining. This has been super, super fun. Cup of Cosmology is back next week. Big thanks to Ali and Lorenzo for joining. I've had a really good time. Hopefully they'll both be back soon. And in the meantime, I hope you all stay safe and take care of each other.